Hello, and welcome to Our Future in Space, where we delve into topics that will define human civilization as we move into the solar system. I'm your host, Dr. Jeff Greenblatt. I'm the Vice President for Science and Research at Orbital Assembly Corporation, and I'm joined here by my co-host, Eric Ward, who is the Vice President of Engineering Design at OAC. How are you doing, Eric?
I am doing great. I'm really excited. Today, we've got a great guest. It is our very own Dr. Shawna Pandya. She's not only the Director of Medical Research at OAC, but she has a storied life as a scientist, researcher, and explorer. Shawna is a rural ER doctor, an aquanaut, a pilot in training, and a graduate of the Scientist-Astronaut Candidate Program with the International Institute for Astronautical Sciences. Thank you for joining us, Shawna. I'm really excited about this. I actually just heard that the Explorers Club named you as one of their Explorers 50, which are 50 people changing the world that the world needs to know about. And we wanted to congratulate you and ask you a bit about the Explorers Club and your involvement there.
Yeah, well, first of all, thank you so much for having me. This is going to be a figurative blast. Yeah, it was a real honor to be named as one of this year's Explorers 50. And really, for anyone who needs a crash course into the Explorers Club, it's all about celebrating exploration with a purpose. So it's not simply just going to a place because, hey, that would be cool, but doing science, publishing along with those expeditions, and making meaningful contributions to what we know as a human species in lesser known areas, whether it's the bottom of the sea or outer space or the jungles or the mountains. And the EC50 is now in its second year, and their whole mandate is to bring attention to the work of explorers across every discipline, every geography, every background, and highlighting the work that we do in our respective fields, and in my case, in space medicine and human spaceflight.
Wow, that's really fantastic.
Yeah,
it's a wonderful honor. Go ahead, Eric.
Oh well, so you just hit the ball out of the park here with your research in space medicine. So I know that you've kind of looked at a lot of fields, but what is space medicine involved? How is it different than terrestrial medicine?
Yeah, that's a great question. So I get asked this question quite frequently, like what these two seemingly disparate terms, space, medicine, like why are they put together? And that's, a really reasonable thought. And then when you think about it, you think about the spaceflight environment and all of the hazards that are associated with astronautics. Simply put, space is trying to kill you. And when we try to kind of catalog that further and say, well, how is space trying to kill us? We broadly categorize the challenges of human spaceflight, especially with exploration class or further destinations, as the big five. So we talk about altered gravity environments, increased radiation, hostile environments, distance from Earth, and isolation and confinement. And so there's a whole host of ways in which we have to consider the challenges of human spaceflight. And the bottom line is pretty much every bodily system, whether we're talking about our bones or our central nervous system, is affected by these five elements.
And then how do you, as a medical doctor, sort of contribute to the development of space medicine? Like, what kind of problems do you work on?
Yeah, that's a really great question. So I've been lucky enough to contribute in a host of ways. So through research, I've written book chapters on psychological resilience in long duration spaceflight, reproduction and sexuality in long duration spaceflight, space spin-off technologies that have benefited terrestrial medicine. I am lucky enough to partake in citizen scientist astronautics research through my work at IIAS. So we're lucky enough to do technology demonstrations as well as technology readiness level increases, for example, through testing various spacesuits in space-like environments. So parabolic flight, the Vomit Comet, zero-G flights, gravity offset. Through one of my other hats as a VP of Immersive Medicine with Luxsonic Technologies, we develop VR medical modules to help astronauts train on medical procedures for long duration space flight. So that's something that we've built for the Canadian Space Agency. And then last but not least, but perhaps most relevantly, pushing the boundaries with our work at OAC. figuring out how we can help further crack the gravity problem. And I hope we'll get into the weeds on this a little bit further this episode. I'm talking about the challenges of 1G versus micro G and the whole black hole of data that remains to be uncovered in between, and figuring out what the dose response curve of human adaptation in various G loads is like. And it's really wonderful to be part of this team, to be taking this problem so seriously and figuring out a sound scientific and engineering method towards cracking the micro G or the gravity prescription problem.
Well, let's get into the weeds in that.
Yeah.
You mentioned this problem with microgravity and the dose response for an artificial gravity somewhere in between 1G and 0G. What are some of the problems with microgravity that you're trying to solve with a dose of artificial gravity?
Yeah. So let's define one of the terms I just talked about, the gravity prescription, a little bit further. So we have billions of years worth of evolutionary data saying how well humans and every other species do in 1G. And I assume everyone tuning into this podcast has the luxury of listening to us from 1G, unless you're tuning in from the ISS, in which case, hello and welcome. And then we have decades of human spaceflight data from Mercury, Gemini, Skylab, Mir, ISS, saying that, well, we know that every single bodily system is affected by the micro-G environment. And so to quickly get into that, we see that from bone loss data that bones without countermeasures will lose 1.5% bone density per month of spaceflight, and we don't see that plateau off. And so we need to introduce things like loading our bones. So when I'm sitting here in 1G, I take it for granted that what the gravity of Earth is actually loading my axial bones and muscles. And so, for example, my pelvis, my femurs, my spine have the luxury of being loaded by 1G. So that actually gives them something to fight against, and they don't lose density, bone density, like they would in space flight. So when you offload the 1G, and you take humans to space, that bone density occurs that doesn't plateau off, can eventually reflect an osteoporotic state like we see in certain populations on Earth. So that's just one subsystem. Other examples, we know that muscles atrophy, and so we need to provide astronauts with countermeasures. We know that without the luxury of gravity pulling fluids down to our feet and then circulating back up, all this fluid will shift upwards. Our heart will, and baroreceptors will interpret this as an increased fluid load. And so an immediate adaptation is that astronauts will tend to excrete out or urinate out more fluid on the first few days on station. Even our inner ears and vestibular and balance systems. So balance is a very finely tuned dance between three mechanisms. So those are proprioceptors in our fingers' ends. So that's kind of how we know where we are in space and what our eyes see, as well as what our inner ears perceive. And so when you get into 0G, there is a whole mismatch, because what your eyes are seeing is totally the opposite of what your inner ear is perceiving. And your brain gets confused. And that is actually a contributor to the space adaptation syndrome. So where people get horribly motion sick for the first 24 to 72 hours on station. And that's actually why no critical activities like spacewalks are planned within the first week of arriving on station. So the list goes on. We know that astronauts are immune suppressed in spaceflight, and that germs are more virulent. So luckily we know that doesn't lead to super infections. We haven't seen evidence of that. We know that most interestingly, over the last 15 years, this constellation of central nervous system findings that has gone through various name iterations, from the intracranial, the VIP syndrome. So that's the neurovestibular idiopathic increased intracranial pressure. And then it's gone now adapted to SANS, space adaptation neuroocular syndrome. And now they're saying, well, there's much more to that than even this specific constellation of findings. But basically, the long story short is the brain juice that coats our brains and spines, that cerebrospinal fluid, doesn't drain properly in space as a consequence of being in microgravity, resulting in increased pressure in our brains around our optic nerves. And in extreme cases, especially in male astronauts, we don't know why, causing flattening of the globe of the eyeball, kind of wrinkling of the backs of the eyeballs, increased local pressure on the optic nerve, causing changes in astronaut vision. So this is like, there's tomes written about all of this, but this is kind of the long-winded answer of how, you know, what we can expect to happen in spaceflight and why we need to better delineate this dose-response curve of what happens in various degrees of gravity. And so what we need to delineate now is the gravity prescription. So what amount of gravity for what duration and at what intervals can help mitigate these findings, especially the space adaptation neuroocular syndrome.
Right, and since you're bringing up that dose response prescription, I guess we're sort of implying that you would have available, you know, partial gravity service or capability on orbit, which is not something that's available right now on any planned space station, with the exception of what Orbital Assembly is doing, which is to develop the ability to rotate and provide at least a partial offset, which would, we think, alleviate or at least contribute to the alleviation of some of these symptoms.
Yeah, that's exactly it, is you know, figuring out what, you know, what level of gravity is enough. Right now we know that this international space community has serious plans to send the humans to the moon, Mars, and beyond. And so part of that accompanying questions that we need to solve come down to, well, you know, is lunar gravity enough to mitigate some of these problems that we've talked about? And if not, is Martian gravity enough? And if not, well, what's the minimum level of gravity? And, you know, if lunar gravity is enough, that is actually very promising for long duration space flight. So, you know, it's really, really promising to be launching partial gravity platforms, especially as a test bed in low Earth orbit, because the research potential and the human health savings and human health potential is massive.
Yeah, well, we're certainly on board with that. I mean, that's why we want to build these things, because, well, it may turn out that we may not need full 1G all the time, or even partial G all the time. Some level of gravity offset, or should I say gravity prescription, seems to be very useful, let's say. And I think, you know, you were also talking earlier about some of these these microgravity adaptation effects being mitigated with in-flight exercise or perhaps some other approaches, but not everything is. Maybe you can just remind us which ones can be effectively mitigated with, I guess, what is generally called countermeasures, to use a basket term, but there are several that are not so well dealt with that way, right?
Yeah, so for example, coming back to two very specific examples, we talked about muscle mass loss and bone atrophy loss. And we know that through countermeasures, specifically resistive exercise on station, we can actually slow down and even mitigate that bone loss, that bone density loss, and that muscle mass loss. So astronauts on station have to do 1.5 hours to 2 hours of aerobic exercise and resistive exercise on station 6 days per week. So the way they do that, there's a treadmill on station called the Colbert, and it's actually named after Stephen Colbert. There's actually a really fun reason behind that. Yeah, it's a fun reason. So back when they were naming one of the new modules to the ISS, Stephen Colbert, turns out he's a massive space and science fan. He got his fans to flood the NASA competition and make Colbert the winning module term. And of course, the powers that be said, well, we probably can't name it after a comedian. But here's kind of our compromise. We will name the new treadmill, the second iteration of the treadmill on station, after Colbert, and they reverse engineered a fancy acronym, exactly, something like combined loaded resistance training treadmill, something like that, and it works out to Colbert. That's why it's named that. So astronauts tether in. They're running on this for 6 days a week, and then the way we get around weights, because there's no point sending 250-pound weights up to the station because that's hugely expensive, and then it's useless and weightlessness anyway. So they have resistive hydraulics that allow astronauts to do squats and deadlifts in 0G. So that's something we currently can mitigate, but there's also trade-offs. Everything in space, as this audience knows, comes at the cost of trade-offs. So 2 hours of astronaut time 6 days a week is a lot to ask when you consider that these folks are highly trained and scheduled down to the 5-minute mark. So if you can save on that, there's a benefit there. And then coming back to the original question is, what haven't we been able to mitigate yet is the SANS, the space adaptation neuroocular syndrome, is a huge, was something that we can't mitigate yet, and something for which artificial gravity has been widely touted as a very real solution. And then, the other part about space is that despite 60 years of human spaceflight, the surprises keep coming. The research of how space is trying to kill us never stops. So in 2019, in routine handheld ultrasound experiments on station, they were just trying to visualize their jugular veins, and then lo and behold, there's a big blood clot sitting there. Like, now we have to ask, well, is space making us hypercoagulable? Is it making us prone to blood clots? And then in January of this year,
and just to interject, a blood clot in that location is potentially lethal, right? I mean, this is not just an inconvenience.
Well, a blood clot anywhere is never great. And then when you see this giant blood clot sitting in your neck veins, so the reason that's important is things need to drain back to the heart, and that includes the blood drainage from the brain. And if you have a roadblock there sitting at the neck, well then blood flow, blood drainage can be, and venous return back to the heart can be impaired. So it's not great. And so the other piece of Canadian research that came out just in January was increased hemolysis, or red blood cell breakdown, in spaceflight. So it's 60 years in, we have a handle on some things, but the beauty and the frustration of science is it's like spilling mercury. You answer one question and 6 new questions pop up.
That's what kind of keeps it fun.
That's where we're at with space medicine right now.
It's deadly, apparently.
So I want to ask a follow-up question about, okay, so it's clear that we're going to need some kind of gravity prescription, and we need to understand this, but adding gravity to what is essentially a microgravity environment is difficult, let's say. I mean, we think we figured out how to do it, fairly affordably, but that remains to be proven. So we're on notice. But what kinds of tools do researchers have right now to simulate, partial artificial gravity on Earth or in other environments, so that we can at least learn something about these effects?
Yeah, that's a great question. So when we talk about how do we simulate partial gravity, we look at analog environments in that they're analogous in some way to the spaceflight environment, and in this case specifically to partial gravity or microgravity. So examples of this, when we talk about the whole spectrum in how we might replicate microgravity and altered gravity and even hypergravity, so increased gravity. Let's talk about the obvious one, parabolic flight. So this might be what many are familiar with as the vomit comet. So you don't even have to fly higher than a transatlantic jet. So for example, a transatlantic commercial flight flies at 39,000, 40,000 feet. When we flew in the NRC, as you see in this photo here, this is with the National Research Council out of Ottawa in Canada. So we're flying on a Falcon 20, and we're flying no higher than 17,000 feet. And so the name parabola comes from the fact that you're actually flying up and down in a parabola. And it's the way you get weightlessness is because when you come over the crest of that that parabola, you're actually falling at the same rate as the airplane. Just like when you're going over a roller coaster, you feel your stomach lifted to your throat. You're weightless for a second, and that's why you feel that way. So now you're falling at the same rate as the airplane, and you get about 20 seconds of microgravity. So in this particular image here, you can see we're testing an IVA, or intravehicular activity spacesuit, and making sure that it tolerates a space-like environment. And the beauty of parabolic flight is, depending on how the pilots fly down that parabola, you can actually mimic microgravity or lunar gravity or Martian gravity, those last two being 17% of Earth's gravity for lunar gravity and 0.38%, 38% of Earth's gravity for Martian gravity. So that's just one example of a gravity test bed. I think earlier we had
great.
Yeah.
I'm sorry to interrupt you. It's great, but eventually you're going to hit the ground if you keep following on this parabolic arc. So you only have what, on the order of 30 seconds or so.
Exactly. Yeah. So that's kind of where the challenge. There's, again, this is going to be a running theme of everything I say. There's always a trade-off. So parabolic flight is limited to 20-second periods of altered gravity. So the continuing along the spectrum, I think you flashed a photo earlier of me in a EVA suit, in a white suit.
Yeah.
And so gravity offset harnesses are another way to test partial gravity or simulate or emulate partial gravity environments. And so in this case, you are in, this is the one. Yeah. So here, this is an extravehicular activity spacesuit, or EVA spacesuit. So this is the kind you would see astronauts using for spacewalks outside the ISS, or the Apollo astronauts on their moonwalks during the Apollo era. And the difference is there's several more layers of radiation and thermal protection and life support built into it, because you're outside of the spacecraft. So the beauty of this gravity offset harness that I'm in is it allows you to input what percentage of your weight that you want to offset, so you can mimic a certain degree of altered gravity. So in this case, we've offset 99% of my weight, so that I'm essentially weightless and in microgravity, and I'm simulating fixing a panel outside of the International Space Station. And we were also able to replicate lunar gravity as well as Martian gravity. And actually, in those test scenarios, we were able to use geologic tools that we designed for lunar EVAs and exploration activities. So, if your wheels are turning and you're kind of saying, well, hey, this has some advantages over parabolic flight, because now your level of altered gravity, microgravity, is not restrained. You can do a 7-minute run if you want, with the trade-off that, well, it's only restricted to whatever's in the harness. So, the tools I'm using still have the 1G weight on them. If I'm practicing a medical procedure, like intubating a mannequin in a simulated weightlessness environment or lunar environment, the mannequin's not in the harness. They're not offloaded. So, there's always trade-offs. Continuing along on your question, what else can we do to mimic altered gravity? So, depends on what you're trying to study, depends on what period of micro or altered gravity you want. So we see human bed rest studies, so head down tilt studies. So you can actually mimic gravity, microgravity, as well as partial gravity by putting study subjects in a bed and then tilting it downwards. So then you're actually offloading the 1G force that exists when you're sitting upright, and see, well, what happens to the bones? What happens to the muscles? What happens to cerebrospinal fluid and the central nervous system when you're replicating that state? So there's the advantage, again, because you can do that for 30 days at a time, and these subjects are paid for their time for being in bed for 30 days.
I hope so. That seems like a really boring occupation. I mean, really, basically you stay in bed for 30 days. You can't exercise. You can't eat normally. Sounds miserable.
I don't think you could pay me enough money to do it, to be honest. I'll be the PI, but I won't be a test subject for that one.
Right.
So, but then you also have to worry, like it's an imperfect replication, because, if when you're in bed for that long, in my mind, you're kind of replicating an ICU patient, because you're at risk of pressure ulcers now, because your subject is in, lying down, they're not able to get up. And, you know, certain activities, so you can see how that leads them to be decompensated because they're not performing any activity during that time. But they're also not performing the kind of activities they would do on station. They're not getting out of bed to, you know, do any operational activities, going to the bathroom, eat. So again, there's limitations, but they're also, you know, great for studying things over a longer period of time. For things like cells and things that are much tinier and more permissive, we can use things like rotating bioreactors. So you're constantly rotating cell cultures in something that's continuously rotating. So there's no fixed gravity gradient. So in that way, you can mimic the microgravity environment.
It's not quite microgravity, but it neutralizes or sort of averages out the force of gravity.
Exactly. Yeah, exactly. And so, you know, it's great for saying, well, how is cell wall structure? How is wound healing or wound healing cells, fibroblasts? How does their behavior change when you're looking at their behavior when you take away the gravity gradient?
So we actually just got an interesting question from one of the listeners kind of on this topic. You mentioned being able to simulate that on the small scale for cells and getting some data out of that. And we have things like parabolic flights and head down bed rest. Using that data and our knowledge of systems like your bones, is it possible to determine what the optimal gravity prescription might be just using that theoretical knowledge and the data that we do have?
Hey, that's an awesome question. There is definitely a budding scientist out there. So yeah, you know, the trade-off is code word for limitations. So, you know, there's the trade-off of saying, okay, let's take, if we want to know how bone cells are going to adapt long-term in microgravity or partial gravity, well, then let's take osteocytes. Let's take these bone cells and put them in a bioreactor for 6 months and see what they do. And that can certainly give you a lot of information about, you know, how these bone cells will react in microgravity versus 1/3 gravity versus 1/6 gravity. But the trade-off is the complexity of living systems. So these are just osteocytes without the complex amalgam of pathways, hormonal responses, you know, in the context of every other bodily system and every signaling pathway. So in vitro studies are very useful for delineating initial pathways and getting the basic science down. But then you have to start building up and saying, okay, well, when you add in real life factors, when you add in signaling pathways, when you add in, you know, osteoblast versus osteoclast, so bone building versus bone breaking down activity, how does that change? So yeah, the short answer to your question is, yeah, it's a very useful way of getting initial basic science information, and it's one piece of the puzzle. And the job as scientists is to kind of, you know, put everything together and kind of Sherlock Holmes your way to the big picture. What are you trying to deduce? What is the big picture of the scientific question?
And so you're saying essentially at some point we're really going to need to go in vivo and do these experiments in a complete human body in that environment to really make sure we fully understand it.
Yeah, absolutely. And, you know, it starts with, you know, science is so complicated because on the one end, you do want to take out any competing or confounding factors and, you know, figure out what the single most important independent variable is. That's, you know, going to help you answer your question. But at the end of the day, we're all complex systems of systems, and then we have to slowly have to add those things back. And so that's why, you know, the big picture of science is looking at that basic science, looking at the molecular level and signaling pathways, and then start building in animal studies and what can we learn from, you know, mouse models and rodent models, and what can we learn from computer modeling, and then finally, bigger picture, what do we learn from human studies? So it's all about piecing it together. And the bottom line is, you know, we still need to do that for the whole dose response curve of this figuring out what the gravity prescription is.
Right. Yeah. So you mentioned, and we've talked a bit about artificial gravity and the dose response of a partial gravity, but you mentioned there were some other big health risks in space. I think you mentioned radiation, the hostile environment, distance from Earth, and isolation and confinement. You know, go into a little bit detail about some of those for our listeners, and tell us, you know, kind of what you're worried about maybe, and where areas for research, you know, that we would want to get done sooner rather than later in order to get more and more people off the planet?
Yeah, that's a great question. Yeah, each one of these things can be, you know, a textbook unto itself. But briefly, the bottom line with radiation is the further up you go, the higher up you go, and the further out you are, the more radiation you have to contend with. So even, you know, being here at ground level versus someone on a transatlantic flight at 40,000 feet, they're actually exposed to more radiation than I would be at ground level. And then that trend continues, so that by the time you're at the level of the International Space Station, what you're exposed to in a day is 250-fold what you would be exposed to versus one day at ground level. And so by the time, so that's why we actually have career and annual limits for astronauts, because we're mindful of that increased radiation. And then when we talk about destinations beyond low Earth orbit, such as the moon or Mars, it's increasingly complicated because in low Earth orbit at the level of the ISS, so 250 miles, about 400 kilometers above Earth, we're still within the luxury of, or the protection of the Van Allen belt. So that means high energy ionizing radiation that comes from solar particle events like solar flares or galactic cosmic background radiation is mostly filtered out. So now that when we go, you know, to the moon or Mars, we don't have that luxury. So then we have to worry about, okay, well, what are our annual limits? What are our career limits? How close are we going to get to them? How are we going to mitigate that? You know, what kind of shielding will we have to build onto our spaceship? You know, ideally we can build a spaceship out of lead, except for that whole trade-off was that's pretty expensive. That's really heavy. Don't do that. And then, you know, there's more sci-fi proposals out there, like genetically augmenting humans to be more radiation resistant or have more protection against radiation-induced DNA damage. And, you know, at the very far end of that spectrum, in the researchers from MIT have argued, well, why not just splice elephant genes into humans? And it's not because we're trying to make an elephant-man hybrid. It's because elephants don't get cancer because they have so many copies of oncogenes, tumor editing genes.
Wow.
Yeah, so it's wild, you know, the things that we're proposing, and there's an ethical argument saying, well, if you're knowingly sending someone into a high-risk environment, don't you have an ethical duty to do everything you can to protect them, including genetic enhancement? And you know, when you look at the argument that way, it's like saying to a firefighter, you know, go into this burning house, but I don't want you to wear a helmet or you know, protective fire retardant gear. And then you're saying, well, that's not very ethical, right? So you know, that's kind of one of these solutions that's being looked at for radiation. Looking at the other three, isolation and confinement. So part of that comes with selection, you know, selecting people who are good at dealing with austerity, these resource limited environments, who look at these types of missions as an opportunity to rise to the occasion, a term in psychology what we call salutogenesis, and also having good interpersonal skills. Like, no one wants to be the person that's voted off the space station. So you have to play nice with the rest of your crew while being mission focused, but also be able to deal with boredom for long periods. So analog studies, like you saw in that image of myself at the Mars Desert Research Station, are a great way of sussing that out. Yeah, so this is what we call real life on fake Mars. This is from the Utah desert. Where they have an entire Mars habitat that looks like life out of Tatooine. And you're essentially living and working with your crew for 2 weeks at a time, bringing your own science. The other thing that we talked about is distance from Earth. So this is going to become a really big contender as we look at destinations like Mars and beyond. Because the further out we go, the longer it takes to communicate. So if there's any Hitchhiker's Guide fans out there, they'll know the Douglas Adams quote that says, "Space is big. Space is so vastly, hugely, mind-bogglingly big you wouldn't believe it." And so the way that translates into sending humans to Mars is even traveling at the speed of light. When Earth and Mars are at their furthest conjunction from each other, we know that round-trip telecoms, like communication, would take about 48 minutes. So if I said hi Jeff from Mars and you said hi Shawna from Earth, and we're at a far alignment, it'll be a 46-minute boring conversation while we wait to communicate with each other.
It's a lot of email and text then.
Yeah, exactly.
Or
So
videograms.
Yeah, and then now
Yeah.
imagine there's something that's mission critical that happens, like a line on the ECLIS system, the life support system blows, and we need to figure out how to fix it. And if we don't fix it in 2 minutes, not 46 minutes, well, it was nice knowing you all. Or if there's like a mass trauma and a mass hemorrhage event on Mars, like you need to be able to fix those problems in situ. And so that's where this whole consideration of distance from Earth becomes a reality as we talk about these far off locales. And then there's everything else which falls under hostile environments. So, you know, we talk about lunar dust, for example. We know from hundreds, if not thousands of pages of documentation from the Apollo era that lunar dust from the regolith was a serious skin irritant, respiratory irritant. It would clog up the joints of the EVA suits. So if anyone ever questions, like, hey, was the moon landing real? They put in a lot of effort by faking the documentation that goes along with it. You know, they paid a lot of attention to that detail. And so, yeah, again, you can simulate in environments like Mars-like environments, like how much of the irritant of an irritant is dust and regolith. And really, when you're in an environment like the Utah desert, you really have to be careful not to track that dust inside because it gets everywhere. And then other examples of hostile environments are altered circadian rhythms. You know, we have evolved to sleep, work, eat on a 24-hour schedule. And then when we look at what the ISS circadian rhythm is, you're experiencing sunrise, sunset cycle every 90 minutes or 16 times per 24-hour period. When you look at a concept like lunar gateway and the orbit is 7 days, that's an entirely different circadian rhythm. And then you're looking at you know, what the lunar day-night cycle at the equator is. It's 14 days of day, 14 days of night. So then you have to say, okay, well, how does that affect sleep, cognition, performance when you take away that what we take for granted here on Earth?
Right. And there's obviously there's a certain amount of adaptation. There's also ways in which we can create a more Earth-like environment, even in these remote locations, right? By creating a circadian rhythm that may be 24 hours or something close to it. But then now you're still talking about something which is essentially in a small sealed habitation environment, right?
Yeah, and I'm
while before we
another trade-off there, maybe.
Yeah, exactly. Yeah. And I'm smiling, Jeff, because you hit on one of my favorite questions that I've started asking of late is, well, why do we have to put up with this? Like, how do we make an austere environment less austere? You know, so how do we, you know, to borrow from Mark Watney in The Martian, how do we engineer the space out of this? You know, and that comes down to, you know, things like engineering the lighting in your spaceship to be more daylight like, not having neon lights, but having you know, more something that would more simulate sunlight, and then fading with and coming on with dawn and dusk like cycles. That's one example. You know, for me this might be a bit of an ask, but it would be nice to have a Starbucks on Mars, like a Mars Bucks or something. That would be less austere. You know, I suspect there's certain limitations to that at present, but I think it's a reasonable question to ask, right? Because we know that there's spaceflight is stressful and that it's busy. So we can also ask the question, well, what if we flip that on its head? What if we bring back certain things that we take for granted, and, you know, make this hostile environment less hostile? And even if that involves bringing back gravity, I think that's a very reasonable and important question to ask.
Sure. Yeah, well, and besides gravity, which is obviously, I think we've established, really important and certainly a priority for what we're trying to do, I'm struck by the images that I have seen, you know, both in science fiction stories, but also in a lot of serious NASA studies of what would an ideal long-term, say, Mars base look like. And you don't see, I mean, obviously you see a lot of scientific equipment and sort of sterilized corridors, but you also see plants, you see mood lighting, you see sort of little cafe tables where people can kind of take a break from their hard work. And really, we recognize just how important these creature comforts are for psychological well-being.
Yeah, you know, one question I started asking is like, well, what if we, you know, to bring some morale back, what if we just sent like a cat to Mars, like as a pet, like have a space cat, you know, for morale? And, you know, it's a reason a reasonable question to ask. And obviously, there's obvious things like, well, what happens when the cat dies? Well, that's will be a bigger, morale sink than, having had the cat. There's extra eclipse usage, there's extra food, there's extra waste. So interestingly enough, I've seen proposals in the past for, well, what happens if you have a VR companion to overcome all of those resource utilization issues, but still kind of bring back some element of companionship that is just there to to bring that emotional support, for example. So
like we could send Tamagotchis up there with all the astronauts to Mars.
Space Tamagotchis, like I've seen, emerging technologies are going to have a really important role to play in future settlements. So a lot of these proposals have been in virtual reality, for example. So again, you're not even taking up space, but because you may already have a headset for other training purposes. And then there's other ways in which we can use technological solutions to, help us with all of these challenges that we've laid out. What if we make more lightweight, radiation-resistant materials and polymers that can help address the radiation issue? What if we engineer medications to be more stable with a longer shelf life? What if we use machine learning to help us with diagnostics for in situ healthcare on Mars? So technology is going to really lead the way, as long as we take into account the need to, really pay attention to the human-machine interaction interface as well.
And I love what you're bringing up with these last couple of examples, because my mind immediately went to, boy, those would be really useful in hostile environments, or at least remote environments on Earth as well. If you had an AI that could help diagnose what was wrong with somebody who's suddenly experiencing a medical emergency, and that's something that every paramedic could carry with them, that would be a fantastic life-saving tool. Right.
Absolutely. Yeah. And actually it's Canada. So I'm Canadian, for those who don't know, and Canada and the Canadian Space Agency's area of priority, and one thing we pride ourselves on in the human spaceflight world, is operational space medicine, as well as bringing those benefits back to our very many rural populations and communities on Earth. And so the CSA has been investing heavily in technologies that can both help on Mars with diagnosis, for example, but also be used for, your most remote Arctic community. And so, for example, some of the projects that we've done with the VR company I work with, Luxsonic, have been funded by CSA, both for exploration class missions, but with a view towards bringing these same medical educational tools back to Earth. So, being able to practice those skills in VR as a physician who's, hours, if not days away from the nearest tertiary care center.
Right. Right. Yeah, I think it's a great example of that synergy, right, between need and technological availability. Sorry, Eric, did you?
Oh, yeah, no, we actually had another question from one of the listeners just pop up when we were talking about Mars and things like, bringing a cat and having, a cafe with trees. And, someone was wondering, what about food? When we're doing a long duration mission like that has a high distance from Earth, we'll need to be growing a lot of that food in situ. Are there any risks that we're worried about or know of about eating food that was grown in space?
That is a great question. And so I should add as a disclosure, one of the companies I'm a medical advisor to actually focuses on that problem, and they're called Astreas. And it's exactly that problem. So when we talk about the challenges of nutrition for space, when I said that microgravity affects every bodily system, I meant it. And so one of the challenges with fluid shift upwards that I haven't talked about yet is all that fluid floating to your sinuses and making you feel congested. And so food doesn't taste as good. It's like you have a cold all the time. So as a consequence, the food needs to be more savory, more textured, but also needs to be lightweight, has to have a long shelf life, be easy to prepare. It has to be be nutrient rich and nutrient dense. So for example, an orange is a thing of luxury versus, you know, freeze-dried dessert that you would just have to, you know, warm up or add water to is kind of what you would more expect. So then when we extend this conversation out to the challenges of Mars, and what the question was asking is, okay, well, anything we bring with us, how do we, you know, get to that 3 to 5 year shelf life? How do we ensure that it can withstand breakdown or spoilage from radiation and or microgravity and or whatever else that comes with the Mars and exploration class mission environment, whether that's exposure to dust. And then, you know, ideally, because transportation is still a very expensive and costly, you know, how can we make ourselves sustainable? How do we engineer food on Mars? And so that's again where we come back to the crux of, well, we really need to delineate this dose response curve of gravity, not just for humans, but for plants. So if we want to create a crop of, you know, wheat on Mars, you know, how much higher will those crops grow in 1/3 gravity? But then what, you know, what is the effect, what is the impact of radiation in that environment? Or do we, you know, 3D print our food somehow by just bringing the basic components with us? So it's a very fascinating problem. And what's really cool is with this company that I'm advising, with Astreas, is they've actually partnered with Aleph Farms, and they've won the NASA Canadian Space Agency Deep Space Food Challenge to actually work on this problem. And there's lots of good entities out there working on it because it's so critical. You know, you can get to Mars, you can engineer the perfect ride to Mars, you can engineer the eclipse, you can, you know, have the astronauts survive all the way to Mars, but if you run out of food, it's going to be a short trip regardless.
Yeah. Yeah, I mean, this of course speaks, you mentioned sustainability, and this isn't really what the focus of this particular conversation is, but since we're in general talking about the large scale, you know, solutions of how do we sustain people in space if they're spending their whole lives there, we're not going to be shipping it from Earth, even if we're just living in low Earth orbit. I mean, maybe if the cost of launch is cheap enough, but it makes a lot more sense to be at least somewhat food independent and learn to grow things in space with the appropriate conditions. So
yeah, well, yeah, speaking about, you know, living long-term in space, you know, I was reading a paper, I think maybe a book chapter that you wrote on psychosocial resilience in spaceflight. Why don't you tell us a little bit about that?
Yeah, that's a great question. Thanks, Eric. So that comes down to, I briefly mentioned this about, you know, the challenges of isolation and confinement, and you know that starts at selection. So when we talk about what makes a governmental space agency astronaut, whether we're talking about NASA, JAXA, ESA, Canadian Space Agency, you know, we look for folks who are very mission focused, but who are also extremely healthy physiologically and psychologically. So there's certain select in, select out criteria, you know, about people who can do their own work, be experts in their own domain, deal with long periods of sustained focus or even boredom, but who can also work well with the crew to focus on the mission objectives. And not everyone's built like that, but we do know from studies in other austere environments, whether we look at submarine life, military deployments, Arctic, Antarctic deployments, you know, living on an oil rig, is that there's people who love this stuff, who rise to the occasion, who view this as an opportunity for fulfillment, self-growth, and this is exactly what we mean by salutogenesis, rising to the occasion. And there's even research about, you know, how we can apply these principles of what makes a resilient person resilient into everyday life to make ourselves more hardy and, you know, cultivate that mental fortitude. And it's an interesting area of the research to look at, given that we're still in a pandemic in 2022, and that we've all essentially been forced to live an austere lifestyle. At one point or another, we've all been forced into isolation that may have not been the norm for us previously. So when we talk about cultivating resilience, or, you know, that ability to deal with hardship or austerity, you know, we talk about mentally preparing ourselves for the best and worst case scenarios, being our own best support network, telling ourselves, we're engaging in positive self-talk, engaging our social network to also help boost us up, controlling the impulse to give in to negative thoughts or to give up. And then just breaking down monumental tasks and thoughts into stepwise, more digestible chunks. And so it's really interesting because, there's a subset of the population for whom, say you put them in, Antarctica for 6 months, and that's, they're as happy as a clam. You say you're going to Mars for 5 years and, pack light, you can bring one suitcase. They're happy as a clam. So it's really interesting to see the psychology. And then on the flip side of it, there's also select out factors that we see at the space agency level. So for example, history of schizophrenia, history of psychosis are select out criteria. And it's this field is constantly evolving as we get more data, but it's simply fascinating to read about and also look at the terrestrial applications.
Wow, it's really interesting how many different areas of this topic you've examined over the years. I'm just really impressed with your depth and breadth. So it's an honor to have your time.
It's really fun for me. Yeah, go ahead.
Yeah, no, it's clearly. I mean, you really lit up about it. We love it. We have a few minutes left, and there's Eric. I don't know if there was another topic that you wanted to that we had discussed earlier that we want to bring up.
Well, we've gotten through the audience questions, kind of as they came up. But I remember reading recently, and I think you've done some research on this. Again, another breadth of topics, on the logistics of reproduction in space and how that part of life is going to be different when we have a long-term community living off the planet. I was wondering if you could tell us a little bit about that.
Yeah, totally. So thanks for bringing that up. And so it's really critical to talk about this, especially for various reasons. So, at the one end of the spectrum, we have space agencies and even billionaires and commercial space companies saying, hey, we're going to send humans to Mars. And we're not just going to go on a one-off mission, but we're going to establish a permanent human settlement there. And with settlement, you're implying generations of humans. So generations implies procreation. So there's, again, that comes back to figuring out that gravity dose response curve, because we know that in 1G, we can replicate, we can reproduce, we can procreate. But even if you're a physician and you spend any time on the labor ward in obstetrics, even 1G obstetrics is scary and has the propensity, or it has the possibility of going sideways really quickly. So then we have to kind of go into the weeds in that and say, well, what happens when we decide to look at reproduction in microgravity or even altered gravity? And then we look at the big picture. It's not just about birth. It's, everything that's involved with reproduction, from arousal to how bodily fluids cohere and adhere differently in microgravity, to how gametes the sperm and the eggs are formed and even released in microgravity, how embryo formation and implantation occurs, what happens with in utero development, and then you get to the scary moment of what happens during birth. What happens if you are having someone give birth in space? On Earth, things can go sideways for any number of reasons. Baby can get stuck. There can be mass hemorrhage. Baby can have a non-recovering heart rate. You may have to go to a stat C-section. So then what happens if you have to go to a stat C-section in microgravity or 1/3 gravity? And then, say you figured that out. Well, what about the neurodevelopment? We know we have lots of insect studies, wasp studies, zebrafish studies, rat studies, and some say that, hey, there is a neuromotor developmental delay that we saw in 3 months in rodents, but then it disappeared. But we saw a higher risk of, or higher rate of wasp death, wasp offspring death in male wasps that were flown to Skylab and came back. And this is real research that I'm quoting, by the way. So when we put all of that together, very few of these are mammalian studies. None of these are human studies. And so then the question is, what do we know? And the bottom line is further studies are needed. And so it's critical on when we talk about humanity's longevity into space. And then, taking a step closer to home. talking about commercial space, you know, we've seen an incredible inflection point in commercial space travel last year and this year. Looking at suborbital flight, looking at orbital flight, and, you know, coming back to our mission here at OAC, we're starting with, you know, uncrewed partial gravity research platforms with a view towards creating the first space hotel. So we know we shouldn't be naive, and we shouldn't pretend that people are going to be on their best behavior and not want to, you know, do what people would do in a normal hotel on Earth, right? So we have to prepare ourselves for the eventuality that even within our own, you know, Voyager station, that people are going to want to, you know, engage in reproductive activities. And, you know, this is something that we should be aware of. And it's also a tremendous opportunity to help advance the research around this, because if we're serious about becoming a permanent off-world multi-planetary species, we have a lot of things to suss out on the reproduction front.
We do. Yeah, I mean, it definitely brings up a bunch of ethical questions, which have my alarm bells going off. I'm thinking, well, wait, can you even do this kind of research? And then I realized everything you were describing was non-human, but still, even with volunteers, you know, it's still, when you're talking about creating life, that gets into a whole other,
at some point, there will be the first human baby born in space, you know, and
yeah. And there's even
hopefully
a company,
not in 0G, but
there's even a company working on that. And so Spaceborne United, so the co-author of the book chapter I wrote is actually an advisor to that company. And initially, so they're based out of Europe, I want to say in the Netherlands. And their initial mandate was to say, well, let's take, you know, a lady in her third trimester and take her up to low Earth orbit to give birth. And then everyone said, okay, but yeah, exactly. We just talked about how wrong everything can go on Earth. So now they're taking a much more stepwise approach, saying, well, let's see what embryos flown in space do. You know, let's see what human embryos that have been donated for research that have passed the ethics board. Let's see how they fare and what anomalies or what differences there are in development, or even even in just the embryo's existence that comes after being flown, compared to an embryo that's you know, just known a 1G existence.
Wow, we obviously have to tread very carefully, but I'm really glad that there are, you know, brave scientists who are thinking about ways that we can still learn something, because it's all extremely valuable, you know, science.
Yeah, it's always critical to always, you know, say, well, how do we do this as ethically and as safely as possible, while still recognizing the need to, you know, answer critical questions that are vital to the end question, or the end goal of becoming a multiplanetary species.
Right, which is the big picture here that we're grappling with.
Yeah.
I have one more question for you. It is another topic, but we can keep it short if you like. Eric, before I ask it, is there anything else on your list you want to?
I think we can go. It's getting up there in time, so.
Okay. All right. Quickly then. Hibernation on a 6 to 9 month journey to Mars. Is it possible to put people into suspended animation, and is that a good idea?
Yeah, so, you know, there's actually, honestly, I honestly like to say that if you have a question about the spaceflight environment, there's someone out there working on that. And sure enough, there are agencies and institutions working on the human hibernation problem. The European Space Agency in 2019 actually ran a study and figured out that by having humans hibernate for the vast majority of a mission to Mars and waking up 3 weeks before landing on the red planet, they could actually save on volume needed for the spacecraft by 1/3. And then there's another company, or another research institute, I think it's the Alaskan Arctic Biology Institute of Research, something along those lines. And what they asked is, well, can you induce hibernation in non-hibernating species? And so we know that the ground squirrel hibernates. And in so doing, they actually reduce their metabolic load to by 99%. So they're operating at 1% of their metabolism, which is huge. Think of the energy savings. Think of the resource utilization savings. So, well, if the ground squirrel can do that, well, why not a distant cousin? Why can't we do that in rats? So they actually managed to induce hibernation in rats But there was a little bit of a side effect in that these guys were more prone to gut ischemia, perforation, sepsis, and death. So there were things to still figure out. You know, and when I think about how this would apply to humans, obviously there's lots of benefits. But if we're talking about simply putting a human in a bed and then just hibernating them for months at a time, we have to look at the context of what happens to comatose and ICU patients and what they run, the challenges they run into when they are, you know, just comatose for that long. So, you know, their muscles atrophy, they're contractured, and they're also prone to breakdown ulcers, pressure ulcers from all of those pressure points that are constantly, you know, in contact with the bed. And there's protocols in intensive care units for turning these patients every 2 hours, but these patients still get breakdown ulcers, you know, on pressure points, ankles, back of their head, their buttocks. And in worst case scenarios, they can get infected and lead to sepsis. So, you know, that's the last thing you want on a mission to Mars, because you want to keep these guys as healthy and ready to work as possible. So then, Jeff, you'd mentioned suspended animation, like in sci-fi that you see, you know, and everything from Futurama to Star Trek, and, you know, it's like, well, we could theoretically get rid of the pressure points if we just kind of hung them in suspended animation.
I was going to say zero G's your friend in this case.
Yeah.
Yeah, exactly. Yeah. And so, you know, I still would wonder how decompensated a human would get from not flexing. Maybe you would have to auto flex, auto extend those muscles, do physiotherapy like you would for patients with neuromuscular diseases and paralysis to make sure that their joints are still working, that they're not atrophied, they're not contractured. But still, if you can justify the benefits of this, it's definitely worth looking into.
Well, thank you. Yes, yes. The topic for obviously more discussion, but I just wanted to make sure we asked you a bit about it this time. Yeah. So, yeah. Well, I think we are out of time, but I think we've learned a lot this hour, and I'm glad that we have so many people tuning in and got some good questions from our viewers, our live audience. Shawna, is there anything you'd like to say in closing?
No, this was so much fun. I look forward to you know, getting the answers to some of these questions, like the dose response curve for gravity, you know, figured out with the OAC team. And, you know, this is really the perfect time in human history to be talking about these big picture ideas, because we're living the future and we get to help architect it. And that's a tremendous privilege that I'm happy to be part of.
Absolutely. As are we. So, all right. Well, thank you so much for your time, Eric. It's been great co-hosting.
Yeah, thank you, Shawna. And yeah, for anyone listening to this, thank you guys for you know, live on showing up and listening to this on your podcast or watching the video on YouTube. If any of you guys have suggestions for future discussion topics, people we might want to interview, or just, you know, comment, or if you'd like to get on our list to show up to the live recording, you can go ahead and email us at ourfutureinspace@orbitalassembly.com. And you can also find us and engage with us on Twitter at ourfutureinspace and Facebook at ourfutureinspace. Thank you so much.
Thank you. Bye-bye.